Our last probability topic is sampling. And this is the same sampling that we talked about in the beginning of the semester. So we have a larger group, whether it's our population or our sampling frame, that we're going to pull a sample from. And there are two ways that we can do this sampling. We can do this sampling with replacement, where after I take somebody out of the population or sampling frame, I then put them back and can potentially pull them again. Or I could be doing this without replacement, where once they're selected, I get rid of them, and now my sampling frame or population is reduced by 1. In sampling with replacement, this is going to be independent. One draw does not affect the next draw because I'm putting the person back and my population is remaining the same. Versus sampling without replacement, this is dependent. This is essentially similar to pulling cards out of a deck. Right? This is why counting cards works in something like blackjack, is the idea that if I know a certain number of face cards have come up, that reduces the probability of me getting a face card because there are not as many face cards left in the deck. So this idea of independent versus dependent is going to matter, and that's really the first step of any of these questions to determine, is this with or without replacement, the sampling. So our first exercise here is about tires that are salvaged in a train wreck. So of these 15 tires that are being offered for sale, 5 of them are damaged, and the remaining 10 are damage-free. We are going to randomly select and purchase 2 of these tires. So here's our random selection. This is what keys me into the fact that this is a sampling question. And we are going to do this for 2 tires. So there's going to be a sample of 2. Very small sample, but it's still a sampling question. So our first question is, what type of sampling is this? Is this our sampling with replacement or a sampling without replacement? So I want you to take a moment, think about it. Should have decided that this is sampling without replacement. The reason being is that I'm purchasing the 2 tires at the end. So I'm not going to just take the tire out, record if it's damaged or not, and put it back into the pile. I need to leave this place with 2 tires, so I can't buy that same tire twice. So we're definitely dealing with a without replacement. So one way to handle these sampling questions is to do this with a tree diagram. So essentially at the beginning we have no tires, and then there are 2 options, right? We get our first tire, our first thing that we sample, and 2 things could happen. We could get a damaged tire or we could get a damage-free tire. And then we could do that break again, right? 2 things could happen. You could still get a damage or damage-free on your second pull, so these are for the second. Same thing here, damaged or damage-free. And then it's just about what these probabilities are. So let's think about this. What's the probability our first tire that we grab is damaged? Well, we know that there are 15 for sale, 5 are damaged, and 10 are damage-free. So the probability of being damaged, well, this is just 5 out of the 15 tires. If I choose one of those 5 tires out of the total 15, I have a damaged tire. Whereas my probability of getting something damage-free is 10 out of 15. So just like in our traditional tree diagrams, these sum up to 1, right? This is all of the options that are available to me as I pull my first tire. Here's where things get different is in tire number 2. So at this point, let me draw some little tires over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 tires. And these are all the sad tires. You can barely see my little sad faces, but they'll have sad faces because those are my damaged tires, right? So in the first branch of the tree, oh no, in the first branch of the tree, when we are here, something already happened in the past. We took and bought a damaged tire. One of these damaged tires here is gone. It's already in my car on the way home. So when I go to do my next probability, I have to think about the remaining 14 tires. What's the probability that the one I grab is damaged again? Well, now there are only 4 damaged tires left out of the total 14. Versus damage-free, there's still 10 of those, right? Out of the 14. So again, these still sum to 1 just like they did before. And then the same thing on the other end, except for the other end, we're going to say, okay, we didn't pull that guy. In this other branch, the timeline, right, we pulled a damage-free tire. So now this is what our 14 remaining tires looks like. 5 damaged, 9 not damaged, right? So there's 5 damaged, and there are 9 damage-free. So the probability the next one we grab is damaged, well, there's 5 out of the 14. And damage-free, well, that's 9 out of our 14. Again, summing up to 1. And then we could figure out the probability of each of these possible scenarios. So in the first scenario, I got a damaged tire and then another damaged tire. This is the darkest timeline, right? I went home with 2 crap tires that absolutely do nothing for me. To figure out this probability, I'm going to need to multiply that 5 over 15. Oops, sorry. 5 over 15 by that 4 over 14. Multiply down my little branch, just like we do in all the other pieces to get here. So we end up with 0.0952. In the next timeline, right, in the next option, we get damage the first time, damage free the second. So this will be, here I'll go ahead and write the multiplication, 5 over 15 times 10 over 14. Which ends up being 0.2381. The next one, we got the damage-free tire first and a damaged tire second. We ended up in the same boat, though. We have 1 damaged tire, 1 good tire that we paid for. And this probability is actually going to end up exactly the same. We're multiplying 5 by 10 instead of 10 by 5, but it's the same thing. And then the last timeline, the last thing that could happen, what we really hope is that we get 2 damage-free tires. And this is going to be the 10 over 15 times that 9 over 14, which is 0.4286. So pretty good probability, right? A little less than half, but decent probability we end up with 2 salvageable tires. But there's still an almost 10% chance that we basically paid for nothing. So that's the tree diagram. And here are the questions that could come next. First one says, what's the probability that both tires will be damaged? Well, all we have to do now is look at our little drawing and decide which scenario had both of them being damaged. And that's this one. Simple enough. We can just pull that straight off the tree. Probability that neither will be damaged. Well, now we're talking about this, right? So 0.4286. And the last one here says, what's the probability that one of the tires will be damaged? And now this one's probably the trickiest because this could happen 2 different ways, right? Both of these exist with us getting 1 damaged tire. So we actually need to add those 2 together. So 0.2381 plus 0.2381. Oops, is 0.4762. Now, normally these questions, when I give them on a homework or on a test, I don't expect you to go through the trouble of making an entire tree. Here's the shortcut for how I do these normally. So normally I first look and see I'm sampling 2 things. So I have 2 events that have to occur. My first tire and my second tire, right? And then I think about what needs to happen for my first and second tire for whatever's talking about. So the first one says they both need to be damaged. So first is damaged, second is damaged. And then I just do those fractions that I was doing just here. I don't take the time to write an entire tree. So the first one being damaged, well, there's 5 of the 15. And then I think about that cute little list of tires and go, okay, if I pulled a damaged tire, there are now only 14 tires left and only 4 of them are damaged. And this is essentially an and question, right? I need this and this to happen, so it's multiplication. We are essentially using that conditional multiplication without even thinking about it, and then we just figure out what that probability is. So same thing would be here. We'd be looking for damage free on the first, damage free on the second. The only one where this gets a little bit funkier is this last one. If only one of the tires is damaged, you need to think about the fact that the first one could be damaged or the second one could be damaged, right? This is the other way I could have written that. So you just do a 2 as a multiplier out in front. This is the number of ways that you can order this. And the other 2 examples, I can't rearrange them, right? Here I can actually rearrange them. It still gives me 1 damaged tire, but the actual event is different. All right, so let's see 2 more of these things. Maybe there's 3. So the next question says that 40% of all calls into an IT department are fixed by simply rebooting the machine. Suppose that 4 calls into an IT department are randomly screened. Find some probabilities. So again, we're taking 4 calls, randomly screening them. So there's our sampling. And I don't have a lot of space here to do an entire tree. In fact, this tree would suck because you'd have to have your first, your second, your third, and your fourth call. And then you'd have the first call could be reboot or not reboot, second call, third call, right? And by the end, you have quite a few options. And it's going to be a giant pain in the ass. So we're going to use that shortcut. So we need 4 things to happen. 1, 2, 3, 4. Now we need to decide whether this is sampling with or without replacement. Now it doesn't say that we can screen the same call twice, and that's actually a really silly thing to think, that we could screen the same call twice. But a crucial piece of what we did before was having our total number of calls, right? Our total number of tires in that case. And here we know that we're pulling 4, but we don't know out of how many. So the fact that we're given a percentage here means that this must be with replacement, even though we technically know we're probably not replacing that call back into the queue and randomly sampling it again. On the test, I'll usually use the word independent. Assume that these calls are independent. And if the calls are all independent, then the probability of a call being fixed is 40%, and we can use that 40% again and again and again without needing to change it. So usually I would have the word independent here as the key that this is what we are seeing. So I'm just going to go ahead and write that, independent. So our first question says, suppose that all of the calls can be fixed by rebooting the machine. All of them. Which means call number 1 can be fixed by rebooting, call number 2 can be fixed by rebooting, 3, and 4. Well, what's the probability of the first call number 1 is fixed by rebooting? It says here that 40% of calls are fixed by rebooting, so that's just 40%, 0.4. What's the probability of the next call is fixed? Still 0.4. So sampling with replacement is actually simpler than sampling without. You don't have to think about how the probability is changing. You can just use the same probability again and again, as long as you've taken the time to give yourself these sort of events and what has to occur. So we end up with just 0.4 to the 4th power, which is 0.0256. The next one says none of the calls. Then we get an at least 1, a not all, and an exactly 1. So I want you guys to take a moment here, pause the video, try these out on your own until you get stuck. So for B, none of the calls means that every single one of these failed to be refixed by rebooting, right? First call, second call, all of them. And if rebooting works 40% of the time, that means 60% of the time it doesn't. So this one ends up just being 0.6 to the 4th power, which is 0.1296. The next 2 are a bigger pain in the ass, but they're actually pretty easy once you find out the trick. So at least 1 can be fixed by rebooting the machine. Well, at least 1 means that it could be 1 fixed, 2 fixed, 3 fixed, or all fixed, right? And this is a lot of pain in the ass. You'd have to figure out all of these different things. In fact, if you had that entire tree diagram that I didn't write out, this is every single outcome except for one of them, which is 0. The probability at least 1 is equal to 1 minus the probability that none of them were fixed. Because at least 1 is greater than or equal to 1, right? And the only thing smaller than that is 0. So these 2 things are complements of each other. And we already know the probability of none because it's what we found in B. We can just do this, which is 0.8704. The same trick works for not all. Not all is a little more obvious. Not all is the opposite of all. So if we know all of them will be fixed 2.56% of the time, not all of them will be fixed the rest of the time. I don't know what that is in my head. And I'm failing to type it into my calculator too. We get out 0.9744. The last one is the only one that's a little bit tricky here. I mean, not that those 2 weren't tricky, but now that you know the trick, they're not as bad. The last one here says, what is the probability exactly 1 will be fixed by rebooting? So exactly 1, that's one that we have to go back to the drawing board for. First one can be fixed by rebooting. The next 3 would not then. Otherwise, if any of those were R, it wouldn't be 1, right? So this is what we need. But how many ways could this happen? Because it's the exactly 1, we have to think about the different orderings, right? They're not all the same, so there's different ways that this can happen. Well, the reboot could happen on the 1st, the 2nd, the 3rd, or the 4th. So there are 4 ways that this can happen. 40% chance the first one fixed by rebooting, 60, 60, and 60. And we just multiplied these all together because this is a this needs to happen and this needs to happen situation. So 4 times 0.4 times 0.6 times 0.6 is 0.3456. All right, so I have 2 more questions where we can kind of practice this a little bit, especially more on the sampling without replacement. But these are all tested in the kitten questions on the homework. Students tend to hate the kitten questions.